Welcome to this explainer. Today, we are diving deep into the absolute miraculous mechanics of the human heart. And, well, what happens when that system misfires? We're going to explore a biological engine that is so perfectly tuned it can run for decades without a single break. But at the same time, it's so incredibly delicate that just a tiny electrical misfire or a blocked tube can bring the whole entire system crashing down.
So here is our roadmap for today's journey. First, we'll cover the 0.8 miracle, followed by pressure, volume, and sound. Then we're going to explore electrical chaos, plumbing failures, when the pump fails, and finally, the autonomic connection. Let's just jump right in.
All right, Section 1, the 0.8 miracle. Before we can really understand the pathology of the heart, we first have to establish a baseline of awe for this perfectly timed engine sitting right there inside your chest.
So assuming a normal resting heart rate of about 75 beats per minute, every single complete cardiac cycle takes exactly 0.8 seconds. Just think about that for a second. Literally less than 1 second for your heart to receive blood, contract, expel it out to your lungs and the rest of your body, and then completely reset itself for the next beat. That means the cycle repeats itself roughly 100,000 times a day. It's a stunning feat of biological engineering. And as you'll see, any discrepancy in this timing can ultimately lead to heart failure.
This 0.8-second cycle is essentially a perfectly choreographed dance. The upper chambers, which are the atria, contract for just 0.1 seconds to sort of top off the lower chambers. Then, those powerful lower chambers, the ventricles, contract for 0.3 seconds to pump the blood out to the body. Finally, the ventricles relax for 0.5 seconds. And what's really amazing here is the overlap. Because the atria and ventricles are resting at the exact same time for about 0.4 seconds, the whole heart actually gets this brief little moment of complete rest during every single cycle.
Moving right along to Section 2, pressure, volume, and sound. Let's look at how the physical mechanics of pressure and volume actually create the recognizable sounds of your heartbeat.
Let's quickly define our core terms here so we're all on the same page. Systole is simply the contraction phase. That's when the muscle shortens and squeezes blood out under really high pressure. Diastole, on the other hand, is the relaxation and filling phase, when the pressure drops and the chambers fill back up with blood. The absolute golden rule of the heart's perfect machine is that the systole of the atrium and the ventricle will never, ever overlap. When one is squeezing, the other absolutely must be relaxing.
Okay, so this is a really crucial point. The sounds a doctor hears when they're listening through a stethoscope, they aren't actually the heart muscles squeezing. No, they're the mechanical slamming of valves and the rushing of fluid. That first sound, the famous lub, happens at the exact millisecond ventricular systole starts. The pressure spikes and the atrioventricular or AV valves violently snap shut to prevent blood from flowing backward. The second sound, the dup, marks the end of systole, which is when the semilunar valves close as blood tries to roll back into the relaxing heart. You might also occasionally hear a third and fourth sound. Those are caused purely by the turbulent, rapid rush of blood filling up the chambers.
So, we understand the rules of this perfect machine now, right? But the dramatic tension really begins when the electricity, the plumbing, or the mechanics fail. You see, the body is a volume conductor, and the heart is its central electrical generator. When things go wrong here, it's not just a subtle error. It is a catastrophic breakdown.
Which brings us to Section 3, electrical chaos and arrhythmias. Let's see how a breakdown in the heart's wiring leads to absolute, unadulterated chaos.
The electrical impulse normally kicks off at the SA node, our natural pacemaker. If the SA node fails, you get a sinoatrial block, meaning the whole heart literally dismisses a beat. If that signal gets delayed or blocked while traveling down to the ventricles, you get heart block. In third-degree heart block, the atria and ventricles completely dissociate. They just beat to their own separate, totally uncoordinated rhythms. Then we have the fibrillations. In atrial fibrillation, the upper chambers fire at a staggering 350 to 500 beats per minute. They're reduced to a useless quiver. But the most instantly life-threatening of all is ventricular fibrillation, where massive damage causes these bizarre electrical complexes. The main pumping chambers just twitch chaotically, pumping absolutely zero blood.
Switching gears to Section 4, plumbing failures and ischemia. Moving from the wiring to the plumbing, we really have to look at the coronary arteries. These supply oxygen directly to the heart muscle itself. Because, even though the heart is literally full of blood, its thick walls need their own dedicated supply line.
And this brings us right to ischemic heart disease. When atherosclerotic plaques, which by the way are accumulations of macrophages, lipids, and calcium, When they narrow the coronary arteries, the heart muscle gets starved of oxygen. This severe ischemia causes the agonizing pain we call angina pectoris. Now, if a clot or thrombosis completely blocks off this already narrowed vessel, the blood supply suffers a permanent arrest. This is a myocardial infarction, a heart attack. The localized muscle tissue literally undergoes necrosis, which means it dies. And when that muscle dies, the pump loses its power.
That leads us perfectly into Section 5, when the pump fails. If the engine itself becomes overloaded or damaged by something like an infarction, we face catastrophic mechanical failure. The medical term for this is simply heart failure.
What's really fascinating and honestly terrifying about heart failure is how it acts like a massive traffic jam backing up through the body's vessels. If the left ventricle fails to pump blood out to the body, that blood backs up into the lungs. This left-sided failure basically drowns the air spaces in fluid, causing pulmonary edema, severe shortness of breath, and frothy sputum. On the flip side, if the right ventricle fails, the blood backs up into the systemic veins. This right-sided failure swells the body with venous congestion. We're talking swollen legs and ankles, an enlarged liver, and visibly raised pressure in the neck veins. Both of these completely disrupt the forward flow of blood.
And when the cardiovascular system collapses entirely, the body enters a deadly state called shock. Now, this can happen in 4 distinct ways. First up is hypovolemic shock, where you simply lose too much fluid volume, think hemorrhage, severe burns, or extreme dehydration. Second is cardiogenic shock, where the heart pump itself is impaired, very often from a massive heart attack. Third is obstructive shock, where a physical barrier, like a massive blood clot in the lungs or fluid physically compressing the heart, blocks the output. And finally, distributive shock. A good example is septic shock from a severe infection, where the blood vessels inappropriately dilate, causing a massive, dangerous loss of blood pressure. In all these cases, the tissues are starved of oxygen, and without immediate intervention, multiple organ failure and death will follow.
Finally, let's look at Section 6, the autonomic system connection. Sometimes the heart's hardware, the muscle, the valves, the plumbing, is perfectly fine. But the software instructions from the brain are completely chaotic.
There is this fascinating group of disorders known as dysautonomia. This happens when neuropathy damages the autonomic nerves that carry information from the brain and spinal cord to the heart and blood vessels. The result is a profound chaotic imbalance between the sympathetic fight-or-flight signals and the parasympathetic rest and digest signals. This can manifest as postural orthostatic tachycardia syndrome, or POTS. With POTS, simply standing up causes the heart rate to soar uncontrollably, all because the autonomic software is sending totally faulty data to the cardiac hardware.
Well, we have covered a lot of ground today, haven't we? From the flawless 0.8-second cycle of a totally healthy heart, all the way to the dramatic breakdowns of arrhythmias, infarctions, and shock. Take a second right now. Just feel your pulse. Every 0.8 seconds, valves are snapping shut, electrical currents are sweeping across muscles, and life-giving oxygen is being propelled through your entire body. It is a fragile, perfectly timed miracle that is keeping you alive right at this very moment. So what will you do to protect your perfect machine today? Thank you so much for joining me on this explainer, and I really hope this structure helped illuminate the incredible science of your cardiovascular system.